Good evening and welcome to Lowell Observatory's year-long celebration of our Lowell Discovery Telescope. It's been 10 years since we saw first light with the telescope when it was first used for doing some science. And in fact, this is a special day, July 21st. It was 10 years ago on this very day that the observatory hosted an event to celebrate the first light. Some 700 people showed up. And the keynote presenter was Neil Armstrong, who was the first person, of course, to walk on the moon, and 49 years earlier had been at Lowell Observatory as part of his training to be an astronaut. So we're really excited to be celebrating the telescope. It's really a marvel of engineering, one of the most powerful telescopes in the world, one of the most versatile. Our former director called it, Bob Millis called it the Swiss Army knife of telescopes because of how versatile it is. So every month, we've been talking about the Lowell Discovery Telescope, or LDT. We'll be calling it LDT. Tonight, we're going to talk to two of our scientists about a certain type of research that's done with it, and that's occultations. My name is Kevin Schindler, and I'm the Historian and Public Information Officer here at Lowell Observatory. And joining me tonight are, I call them our scientists, but they also have, different titles. For instance, Dr. Amanda Bosh, who's been affiliated with Lowell Observatory in one way or another since the 1980s, she is now our Chief Operating Officer. In fact, she's our first ever Chief Operating Officer. And I'm not sure how much time that gives her to do research at the moment, but she certainly has a long history of important research. And then our other person tonight, Dr. Stephen Levine, again, a longtime astronomer. He's also the LDT scientist. He was crucially involved with developing the LDT and commissioning it. And also they happen to be married. And so, gosh, I can imagine what the dinner time conversation is about what is going on in the telescope tonight. It's interesting because you two also have similar interests, or at least some overlapping interests in astronomy research. So welcome to you. Welcome to our viewers tonight. For the next hour, we're going to be talking about LDT, and Amanda and Stephen will ask you about some of your research. I mentioned tonight we're going to talk about a specific type of research, and that involves occultations. So let's start off by just talking about what an occultation is.
Okay.
Thank you, Kevin. Go ahead, Stephen. We didn't figure out who was going to speak first, so go ahead.
In simplest terms, an occultation is when one body passes between you, the observer, and some illuminated source behind you. The reason I put it so sort of generally is because people will recognize that as sounding like an eclipse or a transit as well, and that's where they bear distinct resemblance to each other. But basically, in an occultation case, we take advantage of the shadowing that is caused by an obscuring body passing in front of an illuminated body, and use the light from the background body to learn something about the body that's passing in front of it, or between us and it.
So what are typical bodies for occultations?
Well, you can do an occultation of a really distant star by a solar system body like an asteroid or a planet, and those are very common. There's a number of other types of occultations that people have observed over the years as well. So, for instance, we can also observe the occultation of the radio signal from a spacecraft by a body in the solar system. That has been done on multiple occasions. And many years ago, people, and I think it's still being done, people used to observe occultations of stars by the limb of the moon. Now, the first class of occultations, we're doing those observations to learn about the body that is doing the occulting, so the planet or the asteroid that's blocking the light. In the case of a lunar occultation, where we would observe that to learn about the star that is being blocked. to figure out the diameter of the star and if there's any limb darkening on the star, sort of a change in brightness as you go from the center to the edge.
So you both started occultations kind of in the same source, right? You both started at MIT with a fellow named Jim Elliott. Can you talk about him a little bit and how you got started in this? And then we can, you have some graphics, we'll look at what occultations, how to explain what they are and everything.
Yeah, absolutely. I think that, well, Stephen and I were both at MIT as undergraduates, and that's in fact where we met. And we were both working in the Planetary Science Group, which observed stellar occultations by various solar system bodies, and that's kind of how we got our start. And so Jim Elliott and Ted Dunham, who was an astronomer at Lowell until recently, and in addition, a lot of other astronomers at Lowell, Bob Millis, Larry Wasserman, Ralph Nye. In 1977, they were planning to observe an occultation by Uranus, by the atmosphere of Uranus. And they were using a special telescope known as the Kuiper Airborne Observatory, which was a telescope put into the side of a C-131 aircraft that could then fly above the clouds, which is nice because then you don't get clouded out. And Jim, it was a very careful astronomer. And so even though he knew when the atmosphere occultation was scheduled to begin, he began his observing an hour ahead of time, just to make sure that, you know, he didn't miss anything. Or in case there was anything else that hadn't been predicted, that he could serendipitously observe. And so, and that is actually what happened. During these observations, they ended up discovering that the planet Uranus has a system of rings around it. And, you know, it doesn't seem like maybe it's such a big deal now. We know that Jupiter, Saturn, Uranus, and Neptune have rings, but at the time, only Saturn was known to have rings, and Saturn's rings are very different from the rings around the other gas giants. And so this was really a kind of a paradigm shift in how people thought about rings around solar system bodies. And then Stephen actually worked on some of the occultation work for rings at MIT for his undergraduate thesis. I don't know if you want to say anything about that.
Yeah, and actually that's kind of how I got into it and how I never left, apparently. But I was involved with ongoing analysis of the structure of the Uranian rings being done by several people in the same group. And so we were looking at both the ensemble of available ground-based observations that were there, but we also were lucky that we had the recently done observations, and as Amanda alluded to, there are cases where you get occultations where the source is, for example, a radio transmitter on a spacecraft. And we had the added bonus of having the recent Voyager flyby of Uranus and the radio occultations that were done from that to combine with the Earth-based data. And so it was kind of a very exciting time. The rings we'd only known about the rings for a little under 10 years at that point. And yet there was enough data because people had been so aggressive about following up that we were working on using the occultation observations to actually work out the structure and dynamics of the rings themselves. And you can't really see them. It wasn't until many years later that ground-based telescopes were actually able to directly image those rings. So this was really all structurally, something you couldn't see directly.
It's really a testament to the power and utility of occultation studies that it was discovered by that method before any spacecraft saw them, before any large ground-based telescope saw them. I mean, it's really pretty remarkable. But there were other occultation studies, Amanda, you were involved with, one in particular with Pluto.
Yeah, so at the same time when Stephen was doing his work on the Uranian rings, this was the mid to late 1980s, I was working with Jim Elliott on planning for an occultation by the planet Pluto, and it was a planet at the time. There was, we had predicted, in fact, using some telescopes at Lowell Observatory, the 31-inch telescope, we had predicted that a fairly bright star would be occulted by Pluto in June of 1988. And so we spent a lot of time revising the prediction, because the important thing here is that when you have a star that is being blocked by a planet or an asteroid or something like that, if it's a large planet like Uranus, which is much larger than the Earth, then every place on the Earth will see that star disappear. But with something smaller like Pluto, you have to be in the right place at the right time to see it. Otherwise, nothing will happen. And so you really needed to do a lot of astrometry ahead of time, just figuring out the positions of stars and of Pluto, to figure out where to be on the Earth so that you could see the occultation. And so for this Pluto occultation, we actually, what you learn when you do occultations is how much of the Earth is covered by water, and therefore normally you can't just set up your telescope, drive up someplace and pull out your telescope and set it up because it's covered by water. But we were able to get time on the Kuiper Airborne Observatory. We flew out of Hawaii and then flew south, and were able to observe that particular occultation in 1988. And that was the thing we were looking for, was, does Pluto have an atmosphere? And there had been predictions that Pluto should have an atmosphere because methane was seen in ice form on its surface. And so the assumption was that if Pluto had methane on its surface as an ice, then you should have a small amount of gas above it. And so that would constitute an atmosphere. And so that's what we went looking for. And in fact, we were able to find it. And so we were, it was a very exciting time. And we have some images, so we'll show you what it looks like when a body with an atmosphere passes in front of a star, and what a body without an atmosphere looks like, and what those, how they look different, and how you can tell pretty much immediately that there's something in the air, as the title of our live stream indicates.
So you both were involved with occultations for your entire professional career. And then when the LDT came along, was LDT initially one of its uses going to be for occultations? Was that always planned, or is that something that was developed later on?
Well, I mean, the beauty of it is it's a large light bucket. It's a large telescope. If you put the right camera on it, it's an occultation. Occultation imaging is a possibility, pretty much straight out of the box. It actually turns out that I think the second instrument we put on the telescope was in fact an occultation camera, because we had one and we had the necessary mounting apparatus to put it on an open port early on. So we have been doing or attempting to do occultations almost since the beginning, though we don't do a lot of them in any given year just because they come along somewhat infrequently.
Well, let's start talking about some of the research that you've done with the LDT. And I know you have some images you were going to share.
Yeah, so maybe I should just, what do you think? Should I share one of that? Because it's the first one we have shows you just really visually what an occultation looks like. So basically you're looking, let me just start the share. You're looking at a star. So in this image here, you see this bright star in the middle here, and you can see a bunch of other stars, all around it. And so what happens during an occultation is something passes in front of it. And so that means that it blocks the light from the star. So I'm going to start the movie, and then Stephen, I don't know if you want to talk us through it.
Sure. So this is a slightly faster than real time. There you see the star go away, because in fact the small body that we were studying has in fact blocked or shadowed the star as seen from where we were at the LDT. And you can see some extra stars in the background that you can't see because of the glare. And there's the star coming back. And in a sense, this is instant science, in the sense that really that entire event probably took about 45 to 60 seconds. We need additional imaging on either side of that to help us calibrate the images and so forth. But the bulk of the science we will do comes from literally that piece of the image cube in this particular case. Now, this particular body is a Kuiper belt object by the name of Ixion. And it's one of the larger bodies out on the Kuiper belt. And one of the questions that pretty much hangs over every larger body out there is there the possibility that it has an atmosphere, or that it might have some form of debris or satellite around it? And in this case, occultations are still really about the only straightforward method we have from the ground to try to answer that question. And we don't always answer it, but we can at least make a good attempt at it. And in this case, we were right in the path. And it turns out we were actually very close to in the center of the shadow. And so I will say, watching the occultation at the time, one of the things that struck me in real time was that the star didn't just blink out immediately. You actually, if you watch this slowly, you can see that it disappears over time.
Can you play that again, Stephen?
Yeah, let me play that again.
Yeah.
I'm not sure if we'll be able to see that, but let's try it.
And while this is playing, you had mentioned.
Yeah.
So, yeah.
Yeah. You mentioned Ixion, one of the largest. How big is it?
Well, it's not one. It's
the
not
diameter
the largest.
the diameter is around 700 kilometers.
Right, and in fact, that's based on this particular occultation. But if we could look at that actually more slowly, what you would see is that it actually takes essentially 4 frames, and the frames were some fraction of a second each, for the star to actually disappear, as opposed to in a more typical case, the star disappears between one frame and the next. And my first immediate reaction was, oh my goodness, there's an atmosphere, which the sort of slower dimming of the star is often shown that way. But there is another explanation, and that actually turned out to be the case here, which kind of leads to one of the other sides of what you can do with this, and that is that, in fact, the star isn't just a point source. The star is actually big enough that the object takes a demonstrable amount of time to pass in front of it. And it's from that time of shadowing that we could actually derive the size of the star. This is very much like the lunar occultation case that Amanda referred to earlier, where people were using that to figure out the sizes of stars. And so this happens to be a case where we could use the occultation not only to learn about Ixion, and like I say, from this event, in fact, we derived the diameter being roughly 710 kilometers, but we could also, in fact, roughly measure the diameter of the star, and the star turns out to be the diameter of the star turns out to be 130 times the diameter of the sun. And this is actually a direct measure of that based on the principles of diffraction.
So let me ask this with the LDT. Would you have been able to view this, or view it as well, certainly not as well, but would you have been able to view it with the older telescopes that you did occultations with? I mean, they were much smaller telescopes.
Basically, how well you view it in this context really is a matter of how much light you can collect. Mm-hmm. And so this is one of those cases where almost always bigger is actually better.
Let me move to the next image, Stephen, which has the light curve. So I think that might be helpful.
That would be helpful.
That's not it.
There we
go. So
one of the things you would see, so on the left-hand side is the full light curve from the entire observation. And what you see in the middle of it at about 12 minutes or 13 minutes or so is that the light from the star is simply gone entirely. And
so this line here is just measuring the light from the star.
essentially
It also
before,
happens to include Ixion, but it's, Ixion's is much fainter than the star.
Yeah. And in fact, before anybody even asks, you can't see Ixion at all in any of these images. It's simply too faint.
Mm-hmm.
But if you had a smaller telescope, basically what would have happened is that the scatter you see in that baseline for the star would get broader, because you wouldn't have as quite a good signal to noise. So you can sort of see how the cursor is going up and down to a greater extent. And as your telescope gets smaller, that scatter gets bigger. And so it just becomes a little bit harder to tease out the events. And so this is one of those cases where the 4 meters of glass to collect light really makes it possible to get what we call a very high signal to noise, i.e. the bulk of what you measure is real signal, in this case, the starlight being there and then the starlight going away, not just uncertainty in that measurement. And if you look at the image on the right-hand side, you can actually see literally 3 dots on the way down and 3 dots on the way up, which are the measured brightnesses at those points. And those are the kinds of things that with a smaller telescope, we would probably have lost that information. And so the direct measurement of the size of the star, people would have and did notice from smaller telescopes that the event wasn't instantaneous, but making a direct good measurement of the size of the star would have been much harder.
Mm-hmm.
And I think
so. I guess in this case,
mm-hmm.
Stephen, you could, with this, what you got from this particular event was a diameter for Ixion, diameter for the star, and an upper limit on Ixion's, atmosphere. So basically, you didn't see an atmosphere here, and you could place an upper limit on it. Is that correct?
That is correct. Yeah. The entirety of the behavior of the way the light vanished can be explained entirely by having a star that is simply big enough to be what we would call an extended object at the position of Ixion.
Mm-hmm.
So how do you?
And we do have some. Oh, sorry, Kevin.
No, go ahead.
We do have some data on showing an atmosphere later on that we can talk about. What that looks like.
Yeah.
So what goes into deciding what occultations you're going to look at? I mean, there's several things that go into it. Maybe explain that a little bit.
Yeah, the planning process that we have, we look at how bright is the star that is being occulted. And if it's a bright one, then we would have the potential for getting really high signal to noise like this. And so we'd be interested in that. If it's a faint one, then the signal to noise ratio would be much lower. And so that means the accuracy with which we could measure the diameter would be much less. So then we have to decide, is it going to be worth it? The data we would get, would it improve our knowledge of this body? And then if not, then we might not do it. But then the other thing we need to look at is where is the shadow falling on the Earth? And like I said, most of the Earth is covered by water. And the Kuiper Airborne Observatory was retired, I think it was in 1995. And then right now we do have with SOFIA, the Stratospheric Observatory for Infrared Astronomy, but unfortunately that is being closed as well. So there are limited opportunities to fly over the water, over the ocean, and collect occultation data. So if we don't have that opportunity, we have to look and see, is this someplace we can go? In the case of LDT, if we see a bright star passing where the shadow passes right over LDT, then we are on it. But otherwise, we have to think about, in fact, right now we're looking at potentially traveling in the fall to observe an occultation by Triton, Neptune's moon. So sometimes you just have to go where the occultation takes you. You don't have the ability to move where the shadow is. You have to go to the shadow. So that all folds into our planning and to whether or not we observe an occultation.
So for observing through LDT, do you have some sort of program that's constantly looking for occultations that might be visible from that particular site?
Yeah, so in order to really do all of this planning and make these decisions, we have to know where the shadows will be falling. And so we have a program that where we do something called astrometry, which is just really doing very, very accurate measures of the positions of the bodies that might be occulting stars. So, you know, Pluto or Triton or some of these Kuiper Belt objects or some other objects that we follow. And the reason we need to do that is there have been recent catalogs for the stars, so we know where the stars are fairly accurately. But you know, the bodies, the smaller bodies in the solar system, their ephemerides or orbits are not known to that same level of precision. And so we need to have the star positions very accurately and the body positions very accurately. And so we do a lot of that work at LDT as well, because we can observe occultations by tiny little bodies, and tiny little bodies tend to be really faint. And so in order to do this astrometry, we need a large telescope. So that's what we do on a normal night at LDT. And then, you know, if it comes to pass, then we'll observe an occultation by one of these bodies.
So these are things that you can predict fairly well in advance. I mean, the closer you get, you can refine the measurement, the astrometry, but in general, it's not something like you look out and tonight say, oh my gosh, this is going to happen. It's something you can plan.
Yeah, absolutely. We want to plan this ahead of time. And it can be planned multiple years ahead of time. You know, you may still have some lingering uncertainty that will be reduced as you get closer to the date, but you generally will know more than a year out that this is an event that we're going to be focusing on.
Mm-hmm. Well, you know, this reminds me, Amanda, of when New Horizons was going to be flying by Pluto, and you were, I think, squirreled away with some team members refining orbits. Can you talk about that a little bit? Because that was pretty exciting and timely. And
yeah, I was squirreled away. So let me, I've got some images of that. So let me just move forward, pop through here quickly. We can come back to these if we want to. Our plan, so New Horizons was going to be flying past Pluto. And a couple of weeks before that happened, there was a occultation of a bright star by Pluto that we were planning to observe. And so let me just pause here and talk a little bit about what you see in an occultation by a body that has an atmosphere. So what happens in this cartoon, you can see here's Pluto, and then these are the layers of the atmosphere, and there's more atmosphere down at the bottom and less atmosphere as you go up. So the starlight will pass through the atmosphere, and you know, the thinner layers of the atmosphere, the starlight will pass through almost unimpeded. But as you get down to the thicker layers of the atmosphere, then what happens is the atmosphere acts like a big prism, and it bends the starlight, it refracts it. And so you can see that even though, you know, over here, these two were just really close together, over here, they actually get further apart. So by the time this beam here gets to us way down there at the Earth, then what happens is that light actually gets refracted out of our telescope. And so what we see is the starlight from the star, you know, as Pluto's getting close to it, slowly decreasing. And I think my next image, shows us that. It's a little bit, the quality isn't very good, but this would be the star here, and then it slowly decreases here. It doesn't do it quickly like we saw in that Ixion occultation previously. It kind of slowly decreases, and then it slowly comes back up again. And if the body has rings, we would see that. We can also see some features that indicate special things in the atmosphere, like little increases in light from the star that are due to temperature fluctuations, just really minor temperature fluctuations in the atmosphere. And then if you happen to be right in the geometric center of the body, then of the shadow, then we can actually see the starlight brightening in the middle of the planet, called a central flash. And this is the focusing of all of the starlight by the entire atmosphere, and it comes back. But you have to be really close to the center. So for this particular occultation, we had proposed and we were awarded time on Sophia, which is it's 747 with a hole cut in the center, and I think it's a 2.7 meter mirror put in the side of it. This is the path that we predicted using the Lowell Discovery Telescope. Now you may ask, why did we not use LDT in order to observe this occultation? And the occultation lasts about 3 minutes, and this is what the Earth looked like from Pluto at that time. And you can see that you cannot see the United States here. So it was daylight in the US and at LDT, and so we had to fly all the way around the Earth to New Zealand in order to observe this particular event. And by we, I mean Stephen and some other people, because I was still in Flagstaff doing the astrometry.
Yeah.
I was squirreled away doing the astrometry, because with an airborne observatory, we can refine the prediction until a couple hours before the event. And that's in fact what we did. And we called to the airplane and said, fly 200 kilometers north, because we were able to refine that prediction. So this was the final prediction. These 3 lines here show us the midline of Pluto, and then the upper and the lower extent. So the upper limb and the lower limb. And then these dotted lines were our uncertainty at the time. And so I'm going to hand it over to Stephen. No, actually, let me just talk here for a second. So this is where the airplane ended up flying. So they took off from the airfield in New Zealand here, and then flew around in this, what looks like a drunken path, but it was very precisely planned out, because in order to be able to look at Pluto, you have to be flying in a very specific direction, so that the area where there is a telescope will be pointing at Pluto. And so the pilots were trying to hit this zone here. But in order to get there, they did this path. And the reason for that is they were building in basically some extra time and distance in case we called and said, fly 200 kilometers north, then they would be able to adjust their path in order to do that. Or if we said fly 200 kilometers south, then they'd be able to adjust their path in order to do that. And in fact, what we don't see here is there was actually a little bit of a blip here too, because not only do you have to get to this right spot, you have to get here at the right time. And as they were flying, they discovered that they were a little bit early. And so they made a little blip here to waste a little bit of time so they would get here at exactly the right time. And they did. And then they landed.
So how critical, I was just going to ask, how critical then were those LDT observations that you were feeding to them?
Oh, they were absolutely critical, because they were the ones on which we based this final prediction to tell them where to fly. And what we were trying for here was not only to see the Pluto occultation, but also to get into that central flash so that we could learn about the lower atmosphere of Pluto. And this was really important because with New Horizons arriving at Pluto just a couple of weeks later, it really kind of gave us ground truth. So we were measuring what, this occultation from the Earth, and then we could compare it directly to what New Horizons would see when it would get there a couple of weeks later. And so, yeah, it was without the LDT observations, and those were absolutely critical. We also had some observations from our neighbors and colleagues at the U.S. Naval Observatory. These were all pulled together to really come up with this final prediction to be here. And it succeeded. We were able to see the entire occultation and the central flash. And I think I have, well, here, let me show you this. This is what happens. This is Pluto, and it casts a shadow in starlight on the Earth. And then our goal was to put the airplane into that shadow. And so this is a picture of Sophia. This is the 747 with the door open and the telescope in here. And then here is our light curve. one of them, we had multiple instruments observing this, but you can see the light from the star is decreasing, and it does it slowly, not just in 4 points like Stephen showed you in that Ixion event, but over many, many points. And then you can see the light comes back up here in the middle and then goes back down again and then comes back up again. And this little dotted line here is our prediction of what it would have looked like, the central flash, if there hadn't been any haze in Pluto's atmosphere. And of course, we know that there is haze, and that is what we get for this particular event.
You know, this reminds me again, we were talking about how this is similar to like eclipses, and in the same way, events that you can plan well in advance, but when it's happening, you got to be right on it. And time is critical because it doesn't last very long. And that's a pretty high pressure situation when you're trying to get that all, you know, so precisely.
Yeah, you can see this whole graph here is 5 minutes. And we prepared for years for this 5 minutes. So.
And prepared well.
And yeah, and it wasn't just the LDT, it wasn't just Sophia. There were a number of people on the ground. And Stephen, where were you?
So I was at Mount John, which is a little bit south of Christchurch, which is where Sophia was based for their southern deployment, along with several other people. We actually had observations from 3 separate telescopes on the mountain.
Right. So there were a number of people observing from the ground as well in New Zealand and also in Australia.
So it really is a worldwide network of people working simultaneously, both on and above Earth. The coordination is remarkable.
Well, and sometimes you are not so lucky as to have such extensive preparatory observations, in which case your uncertainty of where the path is larger, and so you compensate by trying to get more people to observe across a greater swath in the hope that somebody catches the event. With a 747 at your command, it's a little bit higher pressure.
Yeah.
Yeah. Let me just see what else we have there. Yeah, that was.
Yeah, if you go back.
I don't know if you want to go back to maybe the LDT, and we can maybe talk a little bit about.
Yep. You've talked about what you did with it, especially that occultation. Then was so exciting, and it was New Horizons was happening, like you said, just after that, and so there was just a flurry of activity around Pluto and this occultation work. So yeah, if you can tell kind of how this works with LDT and how the LDT work, some of the instrumentation and such. Well,
the LDT is, I'm sure we must have described it at one point or another, is about 40 miles southeast of Flagstaff. And basically, we are lucky enough to be able to carry 5 separate instruments at a time, so we are able to use both our normal wider field imager, which is what we use for the astrometric observing. So that's a big enough field of view that we can get, hopefully, the body we're interested in, and the star, and a range of additional stars around it that we can use to figure out exactly what's where and how it's moving. But for the actual occultation itself, we would use a separate camera that is capable of reading out significantly faster. And so you tend to trade off speed for field of view, which basically means, the large field of view camera takes something like 24 seconds to read out, which is, for example, in the case of that Ixion event, we'd have lost the entire event, or we would have gotten 2 images perhaps of the entire event, but 24 seconds would have eaten most of it. Whereas with the occultation camera, the readout time is a fraction of a millisecond. So, something less than 1,000th of a second to read out. But like I said, the trade-off is that the field of view in that camera is much, 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 much smaller. And so we don't have the reference stars for figuring position and motion. And And so the ability of the LDT to carry multiple instruments at once actually makes it possible for us to do both positional prep work, but also even to do position work on the same night that we would observe an occultation, and allow us to get sort of before event images and after event images, so that on the off chance that we either got it or didn't get it, we would also have some images available to allow us to do sort of a post-mortem and understand what was the best fit in, very much immediately around the event as to where the body went with respect to the star. And sometimes what that tells you is that in fact you need to refine the orbit, and it's sort of heartbreaking to find that out after the fact, but sometimes there's no better way to know. And occasionally what it tells you is that in fact the star position is not as well known as you thought it was.
Certainly we've had that as well.
Mm-hmm.
So you can see in this image here, this is of course the LDT with the dome open. Can you see the telescope here? I'm not seeing it. But the holes in the dome here are to allow air through, so you can cool the telescope down to the ambient temperature. And I've spent a lot of time here doing astrometry with my colleague, our colleague Carlos Zulaga, the astrometry division. And so it's a favorite telescope of ours. And so I don't know, Stephen, do you want to tell us what's going on in this picture here?
So this is a sort of an oblique side shot of the telescope to give a sense of the actual scale of a 4-meter telescope. And there is a small person in the lower right of this for scale. Basically on the left-hand side, you have the instrument package for the telescope. The light is going to come in through the dome shutter on the right. It will bounce off the primary mirror, which is hidden inside the structure here, be reflected to the upper secondary mirror, and then back down to the instrument package. It's a relatively compact telescope for a 4-meter telescope. To put it in English units, the mirror is roughly 14 feet in diameter. And that gives us an awful lot of collecting area, which is how we're able to do either fast imaging of faint things or very deep imaging to actually see the very faint things. And I think the next slide actually is a zoom in on the instrument package. Yes, and so what you can see is we've marked where the occultation camera is, where the back end of it is that little gray thing that is in fact sticking out towards us. And then our main imaging camera for the telescope, where we do our astrometric or positional work, is the body sticking off to the sort of going from center to lower left. And that's the housing for the larger imaging camera. And we can switch between the two of those by inserting or removing a mirror to divert the beam between one instrument and the other. And so, like I say, we can use multiple instruments within a night. It only takes a few minutes to switch between them.
And the timing of talking about LDT is interesting today, because it's a time when the telescope is actually out of commission for a short time, because the mirror is being resurfaced. So maybe since it's happening today, and the pictures that are coming back from the process are always fascinating to see them stripping the old mirror off. Can you just briefly explain that, just a couple minutes of what they're doing and why they're doing it?
Sure. Basically, the mirror coating, we grind a very precise figure into the glass, which is used to support that surface, but the piece that actually is responsible for reflecting the light and allowing you to collect it is a very thin coating for us of aluminum on top of that glass. The aluminum is about 100 nanometers thick, which is thinner than your average hair. And the aluminum is exposed to the environment every time we open the telescope up. And so it doesn't last forever. It gets slowly abraded by wind and dust and etched by pollen and smoke. And so once every roughly 5 years, we take the telescope apart, remove the mirror itself, take it over to the next building, and then chemically remove the existing aluminum coating, taking it all the way down to the bare glass, and clean that as best we possibly can, and then they put a brand new fresh aluminum coat on. And we start the clock all over again.
And it, you explain it pretty quickly and it sounds pretty straightforward, but when you think about a piece of glass 14 feet across and only 4 inches thick, and moving that, lowering it from second story to a bottom story, and then transporting it to another building and flipping it, and it's really a pretty remarkable process.
I mean, basically, we schedule several weeks for the whole process. And then a lot of the preparation work actually starts even weeks, if not months before this. We have to assemble the necessary jigs. We have to prep all the various pieces to be ready for it. Clean the chamber where this coating gets done, clean the area where you're going to clean the mirror. And there's weeks and weeks worth of preparation that the staff has been doing to get to the point where we do only a little, where it takes only a little bit of time.
We have to test the crane to make sure that it won't drop the mirror.
Yeah, it's fair to say that the crane actually has to carry the entire back end of the telescope, and that works out to be something like 13 tons or 26,000 pounds. So you don't want to screw that up.
And it's a slow process, right?
It is.
Moving that glass very fast.
You don't want to move fast.
Yes.
Yeah.
And let's just
take
take
we have a question.
Yeah, moment from Keith. He says, looks like the LDT mount is an alt-as type mount. How do you correct for field rotation? And maybe first define for our other listeners what that means, an alt-as mount, and then answer his question.
So basically, it means that the mount rotates around. I mean, it is positioned in what we think of as a horizon-centered system. So it's going to rotate this way around an axis that's vertical. So it's like you would think of having a simple telescope where you're trying to say, look at something in the near field, nearby. And that's your azimuth.
And that direction is called the azimuth. Yeah, sorry, Stephen, go ahead.
And then the second axis is your elevation. And you can see the elevation bearing, in fact, on this telescope. It's the hole that's in the middle, roughly just a little bit above center here. And there's a motor around that hole, and that allows us to go from perfectly vertical down all the way down to the horizon. But the questioner's point is a good one. That orientation of the telescope doesn't naturally compensate for the apparent motion of the stars as the Earth rotates. And for smaller telescopes, what you can do is tip the entire thing to align what for us is the azimuth axis with the Earth's pole, and then simply take out the equivalent motion of the Earth's rotation, but we can't do that directly. And so what we have to do is, in fact, move a third thing. And so in this case, our instrument package, the entire package is on a rotating platform. And so if you're looking at the sky and you see your field start to rise, the field seems to do this across the night if you're looking to the south for us. And it's that extra rotation that our instrument rotator takes out. So we actually have to control 3 axes rather than 2 all the time to properly follow an object on the sky.
And we've got about a dozen minutes left or so. So for those listening, if you have any other questions, write them in over the next few minutes, and we'll try to get to those. Otherwise, let's talk just a little bit more about Amanda and Stephen, the LDT, and using it for the occultations.
But if I might, Kevin, before we move on to that, since we seem to have several questions about what's in the air, it's actually worth pointing out that part of the cases where occultations see atmospheres, you actually can, depending upon how good your signal to noise of your event is, start to make an estimate of what the composition of those atmospheres are. And so if you go back to the early Pluto occultations, when the atmosphere was first discovered, even then people were making reasoned, educated estimations of what kind of molecular composition was in that atmosphere. So it's not just, oh, there's an atmosphere. It becomes a case of, well, if the light goes away this fast, then it tells us something about a combination of what the temperature profile of the atmosphere must be, because it will be at different temperatures as you move through it, but also what the density must be. And if you know something about the density, that tells you what the likely chemical composition is. And
So presumably there are other methods of determining the composition of the atmosphere. So this is another way of confirming some other ways of doing it. I mean, the more ways you have, the more likely you are to be accurate.
I mean,
I would say it slightly differently, actually, because what this occultation gives us when we model this, it gives us the quantity T over mu, so temperature over the mean molecular weight. And so we actually, if we know what that mean molecular weight is, what the composition of the atmosphere is, then we can actually figure out temperature as a function of altitude in the atmosphere. And so we can put into the model different, we can try different mean molecular weights. But if we have other information like spectroscopy of the body, then that will tell you what has been detected on the surface and therefore what must be in the atmosphere. And so you can kind of use all of these techniques together to really get a temperature profile of, at the ground level, the temperature is this. And, if you go 100 kilometers up in the atmosphere, it's something else. One of the things I want to point out here is that the pressure of Pluto's atmosphere is around a microbar, which on the Earth is actually a nice vacuum. But this is what we're actually measuring from, just millions of miles away. Is a barely there atmosphere. And it's you can imagine, why it's barely there is because Pluto is so far from the sun that it's really cold. And in fact, right now, Pluto is getting even further away from the sun because Pluto has an eccentric orbit. Its orbit around the sun is not nearly circular like ours is. It's more of an ellipse. And its closest point to the sun was in 1988, I believe. And since then, it's been getting further away. Might have been 1989, but in any case, but since then, Pluto's been getting further away from the sun, and so it's been getting colder. So we actually expect Pluto's atmosphere to become less and less dense, and for there to be just less and less atmosphere for us to detect. And this is one of the reasons why we keep on watching Pluto and looking for additional occultations to see, does Pluto's atmosphere collapse completely and go away until Pluto comes around and gets closer to the sun again and starts to warm up? Or does it just decrease by some amount? And so this is an open question.
And there aren't that many planetary atmospheres to study, right? So, is there anything else like Pluto that you've studied? Atmosphere.
Well, in fact, one of the best analogs for Pluto is, in fact, Neptune's satellite Triton, and that it is a similar distance from the sun, but less eccentric of an orbit, and it's a similar size, has a similar atmospheric composition and pressure. It actually has a fairly complicated, because of its orbit around Neptune and how that changes over time. The amount of energy that it gets from the sun kind of changes in a way that is predicted. And what we're looking to see, hopefully later this year, is how that affects Triton's atmospheric temperature profile. But other than that, the giant planets have atmospheres. Saturn's satellite Titan has an atmosphere. And then we have been looking at the larger Kuiper Belt objects to see if anybody else has an atmosphere.
It's also fair to say, Kevin, it's not just atmospheres that people end up looking for. There's potential moons. There are a variety of small bodies that have turned out to have rings and debris around them, which nobody expected. One of the canonical cases is the small body Chiriclo, which, if you had asked 15 years ago, people would have said it's simply too small to support a ring system. and at least initially discovered by occultation, because there's really no other way to look for it. So it's a way to probe the regions around these things in a very different way from pretty much any other observational method.
So really, we're at the almost the beginning of seeing things in different ways. You don't have to go back too far. In your early grad student days, I think it was still fairly straightforward. You had, moons or planets, moons, asteroids, comets, and they were all fairly, quote unquote, known. But then with better technology, we're finding that, okay, it's not just Saturn with rings. It's not just the large planet with rings. I mean, we're learning so much that what is typical? What is a typical planet or a typical small body? And that probably is going to change over the ensuing years with all the stuff you guys are doing.
Yeah, absolutely. And, people are looking for rings around planets, around other stars, around exoplanets as well. So it really is sort of an information explosion. And, we are learning more about what exists in our solar system and what exists in other solar systems as well. And I think that for myself anyway, I can safely say that I just did not even imagine the variety of worlds that we have, not just us, but everybody has found just in my career.
And it's funny because it hasn't been, it's been some decades ago that studying planets was kind of passé because we knew everything there was to know. But with modern technology, holy cow, it's a whole field again.
That's right. You make a bigger telescope, you'll find more things.
Yeah, funny how that works.
Yeah. So I'm really, excited to see all of the discoveries that will come from the James Webb Space Telescope, things that we didn't imagine.
Yeah, we have just less than 5 minutes left, so maybe let's just end talking about that and maybe comparing an Earth-based telescope like LDT to a space-based instrument like James Webb. What are the different types of light they're looking at, and maybe just a little comparison.
Sure. I'm going to stop the share here, I think. Mm-hmm. I'm not sure that we need these slides anymore. Yeah. So, okay. So one of the important differences is that the LDT is looking, well, it has a suite of instruments, some of which look in the optical and some of which look in the infrared. But and those are just different wavelengths of light, so different parts of the electromagnetic spectrum. And the infrared is a longer wavelength, and then the optical is. And like I said, some of the instruments that we have on LDT do look in the infrared, current and future. The James Webb only looks in the infrared, and so there's a reason that it's an infrared telescope, and that's because it's trying to look at galaxies in the way far in the past. And I don't know, Stephen, this is more of your field. I don't know if you want to talk about that.
Well, I mean, truthfully, the Webb images that have been released over the last week or so are probably say more than I ever could about where that telescope is going. But part of what makes those so really possible is its ability to look through significant amounts of gas and dust that in the optical you would be effectively obscured by. And so they are looking into, deep into our galaxy, for example, or where they're looking deep into existing other galaxy clusters. They're seeing much more of it, both because of the much increased size of the telescope compared to, say, something like Hubble, but also because of the move to the IR.
And doesn't it give you the ability to look at the redshifted galaxies as well?
Significantly further out redshifted galaxies, and that is a big part of the key project for it. I actually would go back and sort of tie things up a little bit in the sense of saying one of the other things is that all of the telescopes in space are in space above our atmosphere. And if you don't mind briefly re-showing that original video from the first occultation.
Yeah. Let me bring that up again.
Basically what you have there is you can see the effects, dramatically see the effects of the atmosphere as you image something through it. And so if you just watch the field, you'll see it's like looking at something through a fish tank, and the star patterns seem to sort of morph around, and that's entirely due to the atmosphere. And so one of the other advantages of putting a telescope above the atmosphere is that you get rid of that, which leads to both sharper image quality, but also much more stable imaging. So we're looking for the necessary funds to boost the LDT into space, perhaps.
Well, we're certainly in exciting times for astronomy with, James Webb just going up, and we're getting just a hint of what it's going to be able to do. And then, of course, with LDT, which we're celebrating this year on its 10th anniversary, that it's really being used for such a diversity of research. And this occultation research is so important, like when we were talking about the New Horizons mission, but also just basically studying objects out there. It's just a golden era for astronomy, I think, with so many different ways, so many different telescopes that are available. So we're really pleased to be able to talk about LDT, and we're really excited to have you, Amanda and Stephen, on tonight to talk about your research and share some of your expertise. And for those watching, help us celebrate this. Stay tuned to Lowell Observatory's website. There's always new and exciting things going on. And next month, we'll continue our coverage of the LDT 10th anniversary as we actually show footage of the resurfacing of the mirror that Stephen was describing earlier. So we'll have some video of that and describe what the process is and everything. So I think we'll wrap it up here for tonight. Thanks, Stephen and Amanda, for joining us. Thanks to Heather and Maddie behind the scenes for making everything work so well. And thanks for you, those watching. We're really excited to share our research with you, and stay tuned for more exciting news from Lowell Observatory. Thanks, and have a good night.